Okay, so once again, I'm trying to figure out logic. I've tried to go all the way down to material conditionals and immaterial conditionals, also called indicative conditionals, I think. The problem with any kind of a conditional is that a conditional is two propositions that are related to each other somehow. But within each proposition, you've got something that says P implies Q, okay? And then you've got this thing, whether it's that or whether it's whether it's an and or an or, they're still related to each other somehow. So when you've got something that's that complicated, it doesn't really get down to the core of what a proposition is and what it means. I have learned a little bit since the last time I recorded anything. For example, in a true or false system, like a binary true or false system, you're going to run into some limitations because of paradoxes. But I mean, computers are able to handle those by putting those by addressing those paradoxes at a higher level. You don't have a computer going 0 is 1, like off is on. You don't have a computer going 0 is exactly the same thing. You don't get these things at a computer level. Computers at the most basic level, from what I understand, and this is what I'm trying to see, I tried to get into computer hardware, like understanding computer hardware, but in order to do that, I had to understand math. In order to understand math, I needed to understand logic. In order to understand logic, I kind of needed to, well, I mean, that's where I'm at. What do you need to know in order to understand logic? Because I wonder if there's a difference between having a gut feeling that something is right and acknowledging the truth of something. Because I think maybe some of the reason why people continue to struggle with logic is because they've already found the answer that they're looking for, and they're still looking for something else to answer their question. It's like, you've already got your answer. You don't need to keep looking in that same direction. In other words, they're doing a infinite regression where there's not necessarily a need for an infinite regression. And that's where the foundationalists go, okay, you don't, it's fallacious to say it infinitely regresses, because you've already got your answer at this finite point that we as foundationalists are saying is your starting and ending point. Okay, I'm just going to read back what I just wrote down. Foundationalists suggest that there is a finite starting and ending point, which is one and the same. Infinity extends from that point in an infinite number of directions and refers back to the point from an infinite number of directions. There's no regression aside from everything pointing towards the relatively infinitely small starting and ending point. So you've got, let's say you've got a base statement, and then you've got an infinite number of false statements that refer back to that thing. In other words, let's say 1 is 1. It's a tautology. All you're doing is reflexively pointing out that 1 is 1. Is 1 2? 1 is not 2. Is 2 1? No. 2 is not 1. And you can do the same with any symbol, which is, I think, where modal logic comes from, but I am probably completely wrong about that. Where you just insert, I don't know what the keyboard symbol is for it, but any old operator that says to execute some kind of function. And there's an infinite number of functions. So you can do whatever option, you know, with any kind of a statement starting out. If it's not 1, it's going to be false. So what you could do is you could add some kind of a modifying statement that says, well, if you multiply, you know, like if you had some kind of a formula, and there's probably an infinite number of formulas that could say this, but 0 times a number is going to equal 0. So that's still going to be true no matter what. But 0 plus 1 equals 1. So if your formula is number plus 1 and your constant is 0, then it is accurate to say that 0 implies 1. But what you're doing in that case is it's not a true-false system. You've got a 3-valued system. And there's such a thing as many-valued. I don't know if it's not called system. It's probably called many-valued truth functions, maybe? So this is why I need to learn it more, so that I can automatically say it. I don't know why I'm even on this page, because material implication, implication, that's what it was. Anyway, this is a thing that is like too high of a level in order to be addressing without looking at the much simpler nested stuff. In other words, I want to just be looking at this. P implies Q. I don't want to be looking at P implies Q, therefore not P or Q, say syntactic consequence. So that's how you read this. So you'd say P implies Q, therefore not P or Q is a syntactic consequence. So the question is, with a many-valued thing, or maybe I should say, you cannot have a, or actually the problem with the paradox is not that the system is wrong. It's that you're making a new rule in addition to that system. You're saying, okay, yeah, I know those are the rules, but I'm not going to abide by these rules by making this statement. In other words, I say heads or tails, and you say edge of the coin. Well, I didn't give you that option. You're adding a new thing in there. Well, actually, no, it would be more accurate to say, well, I want heads and tails. Well, that's not an option I gave you. Well, I want it to be a 3-valued system. I want you to cut the coin in half and put the heads and the tails both up at the same time. That wasn't an option that I gave you. But if you want to play by those rules, then we can say that if it's just one, then you don't get it. If it's just heads, then you don't get what you want. The phrase, this statement is false, the implication in that sentence is that this is a 2-valued system. You can either have one or the other. It's going to be exclusive disjunction. So I'm not allowing you to pick both, but here's a both. You just said that it was this, so you're contradicting yourself. You can't have both. What you're actually saying is that it's a 4-valued system. Is it 4 or is it 3? What you're essentially doing when you're saying that is, I have a system that has 2 values. But here's the third value, that it can be both. And your thing can be both wrong, both true and false. All right, look. This 0 is point. See, the thing is, with with the liar paradox is you're going any statements made are of a two-valued truth function. But what it doesn't say is what happens to statements that are not two-valued truth functions. So it is possible for this thing to be both. So that's a simple way of resolving it. Well, no, it's not, because I'm still getting something wrong here. So does this fit in with that thing? See, in this, what you're saying is it's a one-value truth system. In other words, a single value truth system. 0 implies 1. So really, it doesn't matter what the true or false thing is. It could be this statement is apple, or this statement is orange. The problem is that you've got a statement that is internally, it's self-referential, and it's self-contradicting. When you have a system, it's got to operate consistently according to its own statements, or it really isn't a system. In other words, all systems of logic must operate consistently. Or else it really isn't a system of logic, it's a system of falsity. A system of illogic. But does this mean it's a single-valued truth system? No, because it's saying 0 implies 1. No. When 0 implies 1, so what we're doing here is we're populating the values. We've got an empty variable and then we're filling it in because we're going actually it would be simpler to put this one first. Okay, so let's see what we got. The following set of statements defines a set that is a theoretic closed system that operates according to its own rules. All statements made are of a two-valued truth function. All statements that say they are equal to 0 are also equal to 1. In other words, if x is equal to 0, then y is equal to 1. X is equal to statement A, y is equal to statement B. So a graph of this would just have a dot at 0, 1. Statement A is this statement is equal to 0. Statement B is that statement A is equal to 1. So run it like a computer routine, like a loop. So what we see here is that it's no longer a two-valued truth function. We've got a third. What you're saying is all right, so what we've got here is let's call this function potato. So now what? What do we do with this? We can see that's what's implied in it inherently. That any statements that do not match with that system are to be rejected. They aren't in the system because it's a closed system. Because it is a closed system, it can only accept statements that operate within those limitations. Actually, let's call this basket. Actually, basket is inaccurate. Let's call this fruit holder. Because it can only hold one fruit at a time. Single fruit holder. Because a basket would be something which could hold 3 values, in apple and orange or both. So I'd better type that in there too. So what you're saying is here it would be see, what people don't realize is that the statement isn't as small as it looks at first glance, because there are assumptions that are part of the syntax. Well, they're not part of the syntax. They're part of a lower level of communication that sets something up prior to the higher level of communication. And when people try to make a statement that plays a trick on those lower levels of communication, then what you get is a problem. You get misunderstandings, you get misinterpretations of something, because you're not consistent. It's basically you're lying about what system you're using. So let's say I've got a three value function. It's either going to be, I've got a 2 fruit holder. It's either going to contain an apple, an orange, or both. If I say this statement or the thing in this fruit holder is an apple, and then say right after that the thing in this fruit holder is an orange, there's no misunderstanding there. You go, okay, well, you're saying the thing in this fruit holder is both, or there's 2 things in this. But if I were to say the thing in this basket is an apple orange, you go, well, what's an apple orange? Are you saying it's a hybrid between 2 fruits? Well, no, an apple orange is defined as an apple sitting next to an orange. Well, that's pretty lame. Could have just been more clear. So the problem here is not that it's paradoxical. The problem is that it's linguistically incorrect, or not linguistically. It's probably semantically invalid. It's not that it's logically invalid. It's just it's semantically invalid. You're saying, I want the statements in this system to be statements from another system. You're saying, okay, well, you can't have 2 systems going at the same time. You got to make up your mind and stick with it. So I mean, is there like a law in there you could condense that down into? In other words, you could say all logical systems, no, all semantic In other words, you've kind of got a buffer overflow. With the liar paradox, because you've got more terms than the system was meant to hold. I don't know what buffer overflow is, but it kind of sounds like it makes sense a little bit. It'd be like saying, okay, I have 2 fruits in this container that was meant to hold 1 fruit. Well, did you cram another in there? No, it still only has 1 fruit. It has 1 whole entire fruit in here. Did you cut 2 fruits and put them within there? No. Well, then you don't have 2 fruits in there, dude. You just have the 1. I can express this more clearly. for a logical set, okay, so let's say I have a pickup truck. Let's say in theory that I had a pickup truck of the exact same size and could fit it in there. If that were the case, then really you're not talking about another pickup truck, you're just renaming the set. Okay, so again, let's say you have a pickup truck. You can carry a bunch of crates in there. You can carry just one crate in there. What you cannot carry is a flatbed in a pickup truck. And don't get distracted here by the analogy. Just stick with me. You can also have a container all the way down to one that carries 0 or 1 fruit. But that smaller container, if you try to put a larger container in it, it's not possible. You're going to have a bad day if you try to do that. So by saying that this is a law, here, I mean, this is getting into set theory. So is set theory more foundational to logic than logic is? I think maybe this is just a portion of logic that fits into set theory, but I don't think it's the root. All right, so changing gears here for a second. I think the way that logic works, and maybe this is getting into learning theory, but people talk all the time about, I mean, this is getting to a point where it's no longer theoretical, well, it's no longer a study in the logical or philosophical sense, because you're not going to resolve it with philosophy. you've got to resolve it with like a science, an actual empirical science. Because when you're talking about how people learn, you have to actually look at, you know, genetics and environmental influences, and how people communicate. You've got to do studies and sociology. In other words, you have to do the higher level sciences before you can work your way back down to a point where you can recursively talk about something, where you can talk about the actual core ideas that somebody is thinking about, the empty variables that you've got to fill with ideas and you know, formulas and stuff. How long is this recording so far? We've got another 11 minutes. I just want to stick to an hour. Because all this stuff, all this is talking about stuff with 4 terms at least. You're saying and maybe that's a fallacy. Because, you know, when you're talking about something with 4 terms, okay, so you've got 3 terms here. P is partly the same as Q. See, here you've got a system of 3 values. You've got A is it, B is bear, and C is swim. And within P, you've got A and B. And within Q, you've got B and C. So you've got 3 terms. It's a logical syllogism. Is it gism? Might be gism. I think it's a hard G. Not like a J sound. But do those 2 or 3 statements necessarily have to have a shared third term? In other words, you could have the moon is cheese is equal to P. Q is equal to a completely unrelated thing. So this could still be a, in terms of logical form, it's neither true nor false. Because the form itself doesn't say anything about whether or not the syllogism is true. It's just saying this is the form. In other words, it doesn't matter what the terms are as long as the form is correct. So you can't really get any truth value from rules of inference. Well, no, that's not really totally true, because you could say if P is true, then Q is false. What it can't do is it can't tell you the truth of the substatements within that statement. I'm just going over what predicate logic is versus propositional logic. The predicate logic is a lower level than propositional logic. Propositional logic involves a group of predicates, and it can't really tell you the truth of whatever composes those individual propositions, or those individual predicates. The propositions can't tell you, because they're in a big group, they can't tell you anything about what's in that smaller group. And that's part of why the liar paradox is false, because you've got a larger group that's trying to make a truth value statement about a larger group. No, about a smaller group. In other words, you're trying to express something in terms of its holders versus what's in it. Is it that way, or is it the smaller components making a judgment about the larger one? In other words, if I say, I've got an apple, Therefore, this container is a 3-fruit container. That would imply, like, what? Six, 7 different possibilities. I don't know what it's called when you do that operation. I guess if you had this, it would just be whatever thing you've got plus 0 as a possible option. Well, that's good news. 2 plus 1 plus a third option. Looking at probability versus that's not right. So if I've got a 2-fruit holder, it can either be 1 fruit or 2 fruit, or swap those two values. 1, 2, 3. 1, 2, or none. So yeah, that makes sense. And if it's a 4-fruit holder, it's going to be 4 or 3 or 2 or 1 or 0. Wait, that makes no sense. Oh, okay. So I'm not just suggesting that there are a certain number of values within that thing. I'm talking about each one having a unique value. Okay, I think